Thank you for the introduction, and I'm very happy to talk about our recent progress. It's based on the collaboration with Huang Zichang, Kong Lianxi, and Wang Yidun. So the talk is about the Anyon condensation and Goldstone's theorem. So about the Anyon condensation, it's a relatively new concept or idea in recent years. So it's better to compare it with more well understood concepts in history. So here, let's look at the BCS superconductor. So this picture shows it's an illustration of the superconductor in a magnetic field. So this BCS superconductor has the following features. It has the electrons. Electrons cannot condense, but electrons can form Cooper pairs, and the Cooper pairs can condense. And it has a macroscopic coherent state. And this picture shows its experimentally detection of the density states in the momentum space. So it's an illustration of the condensation. And the BCS superconductor has another feature. It has the spontaneous symmetry breaking. It has the U1 global symmetry, but this symmetry is spontaneously broken in a condensed phase. So when we compare the Anyon condensation and the boson condensation in condensed matter physics, a basic question is there a counterpart of the phenomenon and properties of superconductor in the topological phase? So let's look at a simple example, the torical model. In this model, we have anyons, the Z2 charge E, Z2 flux N, and the charge flux composites. So we already know how to use the condensation data to classify the topological numbers in Anyon condensation. So the condensation data is a Frobenius algebra A and its representations in the topological phase. So here in torical model, after the condensation, sorry, I should mention that here the data, the Frobenius algebra A is it consists of the Z2 charge E. So it's a direct sum of 1 and E. It means this is a Z2 charge condensation. And after the condensation, the topological numbers are given by the A and B, which forms the representations of the Frobenius algebra, and here B is confined. So this is the algebraic way to understand the topological numbers in condensed phase. Now in our construction, we will do the following to construct an effective Hamiltonian. So first, we need to define a Hilbert space. So the Hilbert space should contain all the observable states. So here, what we can observe in our model are the anyons. So our Hilbert space should contain the states that incorporate the anyons 1, E, N, and En. So we define a basis by the anyon species. J1, J2 means the anyons at the position 1 and 2. And the next step, we will define a creation operator. This creation operator, Wn E, will create a pair of the Z2 charge. One of the charge is inserted to the system and fused to the Anyon Jan at the position n, and the other Z2 charge is it's also insert to the system, but it fused to the condensate. Then the Hamiltonian has an extra term, which is the creation operator here. And the result is the following. So this Hamiltonian gives us the condensed states. Here, in the convention, the capital V is a superposition. So the capital A is it's 1 plus E, and capital B is M plus En. So in this way, So in this way, we have constructed the Hamiltonian approach. And the features in this approach is we can construct the coherent state formulation of the condensed states. This will in this way we develop the same framework for the Anyon condensation as well as the traditional coherent states for the boson condensation in condensed matter physics.
Can I have a question?
Yes.
So I'm a little confused about what kind of a space you're dealing with. So when you mention condensation, does it condense in, for example, momentum space, or does it condense in this Hilbert space that you defined in the previous slide?
Oh, here, in this slide, we use the momentum space, and what kind of condensation, what kind of shape, or what kind of distribution in momentum space is given by the parameter theta k. So I did not mention any specific way. So here, the AK is the bosonic operators in momentum space. And this is the theta is the coherent state with the parameter theta k. And this coherent state can be written in this way with the exponential of the creation and annihilation operators. And this exponential is an operator. This is called the Bogolov transformation. This is the coherent state formulation to understand the condensed states, like superfluid superconductors or ferromagnetism. In our case, in the torical model, we have the generalized coherent states in our construction. So in the following way. So we have just mentioned that by solving the Hamiltonian, we obtain the condensed states with A and B's as our new quantum numbers, but there are much more degrees of freedom. So that means we have not just capital V's, but we also have the V, G. So here we use a transformation UG, which is a Z2 transformation. So which means the topological numbers A and B carries they are equipped with the Z2 transformation, and all these topological numbers A and B together with the Z2 transformations, they form the degrees of freedom in our Hilbert space, and in this way we can formulate the generalized coherent states. Then compare with the coherent states using the bosonic creation operators. We use the W as the creation operator, and the coherent states is defined as the eigenstates of this creation operator. So using this coherent state formulation, it gives us an illustration comparing the order and the symmetry. So I use the hidden symmetry because when I say symmetry, it's the broken symmetry, and and acting as the hidden symmetry on in the condensed states. So in this, we compare the Z2 anion condensation and the boson condensation. The coherent state in the boson condensation is given by a Boglu-Bol transformation, which is expressed as the exponential here. Then in Z2 topological phase, we have we can compare all these concepts. So the Z2 elements, small g, it's just like the theta in the above. So g is our parameter of the coherent state. And UG, the Z2 transformation, when we compare the formula, UG is our Boglu-Bol transformation. And also we can try to look at these concepts from a representation perspective. So theta. So the Z2 elements, small g, it's just like the theta in the above. Oh, okay. Okay, let's continue. Yeah. So theta, these are distinct representations of the canonical commutation relations, which means theta, these condensed states, they are in a Fock space. And each theta specifies a representation of the canonical commutation relations. And here Vg similarly is specified a distinct representation of the Frobenius attribute A in a topological phase in the modular tensor category C, characterized in a topological phase. So that means from the representation theory perspective, we can directly compare these theta and G. Both theta and G, they labels the representations. All right. So this means this coherent state formulation it's a quite good platform to study to compare the order and the hidden symmetry, which is complementary concepts in a study of phase and phase transitions. Okay, so I have just mentioned the features of this constructor about the coherent state formulation, and our effective Hamiltonian approach has another feature. In this construction, we can study the symmetry breaking. That means when we look at all these operators, the creation operators, these operators are invariant under the global symmetry. In our case, this symmetry is to preserve the charge Z2 charge numbers. Then right with the symmetry explicitly written down, then this is convenient to study the spontaneous symmetry breaking, which is very important in the condensation phenomena. Okay. So I have just talked about the basic steps to how to construct the effective Hamiltonian, and now let's check if we did find the counterpart of the phenomena and properties of the superconductor in topological phase. In the BCS superconductor, we have the condensation of the Cooper pairs, and in the Z2 case, in the toric model, we have the condensation of the Z2 charge. And we also obtain the coherent state description of the condensed states. In our case, this coherent state, it's a superposition of the vacuum, the original vacuum and the Z2 charge. And for the spontaneous symmetry breaking, the broken symmetry is a Z2 transformation, which maps the 1 plus E to 1 minus E. So, yeah, so we have so we have written down all these concepts about the coherent states and the spontaneous symmetry breaking in the toric Anyon condensation. We can look at the coherent state more closely. So when we have defined the creation or annihilation operator W in this way, then we can write on the coherent state, which describe our condensed states. We denote them by psi plus and minus. This plus and minus, they form our vacuum space. So, yeah, as written down here explicitly, these two states has the following meaning. If we insert a Z2 charge into the system, the wave function obtain a phase, which is e to I theta, taking values of plus minus 1. So this is how the macroscopic coherent state look like in our toric model. Okay. So another feature is this coherent state formulation gives us an illustrative picture of the condensation data. So we already know the Frobenius algebra can be used to classify the topological numbers in Anyon condensation, where the sub-objects of A are the condensable anyons. But what is the multiplication in the Frobenius algebra, and what is the modular action in the representation? So the multiplication product structure it actually describes the way how to insert the condensable anyons into the condensed states in our state. And in the representation, it specifies the way how to insert the anyons and fuse to the existence anyons in our system. All these describe the behavior of the macroscopic coherent state. Okay, so we have just talked about the effect Hamiltonian approach for the condensation in our toric example. Then the question is, can we do a general construction? So what we need to do? So first, I think we need to consider the two principles. The first is what kind of Hilbert space we should define. The first principle is the Hilbert space should contain all the observable states. So that means the Hilbert spaces should contain all the topological numbers describing all anyons. And secondly, it's the symmetry principle. That means the Hamiltonian should be invariant under the original quantum group symmetry. So by the quantum group symmetry, what I mean is in the topological phase described by a modular tensor category, we assume the system has a quantum group gauge symmetry and so it has the quantum group global symmetry. So that means when we design the Hilbert space, all bases should be invariant under this quantum group symmetry. And in general construction, which means all the Hilbert space bases should be written as the morphisms in the modular tensor categories. So as a result, the Hilbert basis can be written as like a fusion tree here. So this fusion tree is it means it gave us a basis to describe the anyons in the Hilbert space. But there is a problem. So is this all we need in the Hilbert space? There is a problem due to the spontaneous symmetry breaking. So since in the condensed phase, there is a symmetry breaking, then we need more degrees of freedom than what we just have talked about. This is due to the Wigner-Eckert theorem. It says if we have a symmetry, we need only the degrees of freedom corresponding to the representation labels. But if the symmetry is broken, then in addition to the existing representation labels, we need to consider the representation matrix index. So this is what we already know in the angular momentum theory. So this means what we just mentioned, the basis in the previous slide is not enough to construct the Hilbert space to describe all properties in the condensed phase. And we need to find a way to get more degrees of freedom. And the way is to define the desired Hilbert space basis is to use the Tanaka reconstruction theorem. It says we can reconstruct the glue transformations from representations. And the equation below is in the graphic. It means some tensor equations, but basically, its meaning is that we can use a more familiar case in a finite group case. Is that what it means is if we have some CG coefficient for any finite group, if we know all CG coefficients for all representations, then we can reconstruct all group transformations from just the CG transformations, which means if you know all group elements, you know the multiplication table, you know this group. But equivalently, you do not know the group elements, but you know all CG coefficients or 3J symbols. You can equivalently obtain everything you can get from group elements. So in our case, if we know the condensation data, we know what kind of condensation is, then we have the Frobenius algebra, we know the multiplication structure in the Frobenius algebra, then we can reconstruct the group elements, which provides us the degrees of freedom in the Hilbert space, as well as the group transformation, the symmetry transformation in the condensed space. So the idea is the Tanaka reconstruction theorem says we can reconstruct the group elements from representations as long as we have a fiber functor, but we will use another formulation, which is discovered by Muger and other people. It says, they say, if we have some good Frobenius algebra, then we can have all information to reconstruct the glue elements from representations. So this is the way we will do in our work. So in this way, we get all the degrees of freedom in the Hilbert space, and we also obtain the symmetry transformations in the condensed phase. Then we obtain a coherent state formulation for the condensed states in general case. So in this formulation, the Hilbert space has two types of degrees of freedoms. This one is the yes.
雨婷，
Yes.
我这儿问个问题可以吗？
可以。
就是你前一页，一个问题是你那个 Muger， 你这个最底下一行有一个方框，你有一个 Muger 那个定理，就是 absorbing Frobenius algebra。absorbing 是什么意思啊？
Oh, observing means it has some constraint. It says Frobenius A multiply itself. The A tensor A should be multiple copies of A.
OK，第二个问题
Yes.
，OK， 第二个问题就是
So I did not mention this detail since this is in. If we consider the boson condensation, then this property is enough. So but thank you for the question.
OK， 我第二个问题就是你用这个 Tanaka reconstruction theorem， 你说你可以 construct 这个 group， 你 construct 这个 group 是symmetry breaking 之前的那个大的 group， 还是 symmetry breaking 之后这个 unbroken 的那个subgroup？
是 broken 的 group。
你说是 broken 的 part。symmetry breaking 之前你有一个大群，对吧？然后你
breaking 之
symmetry
前的大
breaking
群
之后，
是
你就应该有一个 unbroken 的子群，那是个小群。
啊，在这里就是之前的我应该可以叫量子群，是所有就 condense 之前所有的拓扑量子数所对应的那个对称性是 broken 之前的。
OK，
condense 之后的是在 condense phase 里面你所能观察到的所有的拓扑量子数对应的那个对称性叫 unbroken symmetry。
OK， 所以
然后global
你说
symmetry broken 了，那这个 reconstruct 的 symmetry 就是这个 broken 的 symmetry， 所以我这里就写了叫 hidden symmetry。在前几页写的是 hidden symmetry。
hidden 的就是 unbroken 那个是吧
？hidden 是 broken 的那个，看不到了。
OK， 你继续讲吧 ，Thank you。
Okay, so we obtained a general construction of the coherent state formulation of these coherent states. So since this is since we can write down all these states in a many-body system, then we have all the degrees of freedom we can use. So in this general case, we obtain the generalized coherent states. The group elements G So it's the first type of degrees of freedom in the Hilbert space. And the second type, degrees of freedom in the Hilbert space are all the topological quantum numbers in the condensed phase. So here we also do the comparison again. So so for each parameter G, we have the group transformation labeled by UG. So compare with the coherent states in the boson condensation example, it corresponds to the Boglu-Bo transformation. So, and this capital V, the second type of degrees of freedom in the Hilbert space, they are all labels in the representation category of the Frobenius algebra in C. So we have a comparison, namely the C, the modular tensor category C is analog to the canonical commutation relations in boson system. And our symmetry transformation, UG, is comparable to the Boglu-Bo transformation in boson condensation system. And the Fock space built on the coherent state theta is corresponding to the representation category rep A in the condensed case, in the Anyon condensation case. Okay, so obtaining the Hilbert space, and we can write down, yeah, and we can also define the creation and annihilation operator W. Then using this effective Hamiltonian, we can write down the coherent state formulation of the condensed state. And we can also write down the symmetry transformation on this space.
Excuse me.
Yes.
Maybe just a quick question. So, is the Hilbert space in this of a subspace of, or it's just an abstract space of this equation?
In toric model, this Hilbert space is the same size of the original Hilbert space. So, which means in toric code, we have the quantum numbers Z2 charge E, Z2 flux N. So it's like 2 copies of Z2 labels. In our formulation, we also have two copies of Z2 labels. The capital V's, which are the topological numbers in the condensed phase, cap A and B, and we also another copy of Z2 labels, which are the glue elements describing the hidden symmetry or broken symmetry. So they are of the same size.
So, if this new Hilbert space, and the basis of the new Hilbert space, do they look like the Fourier transform version of? Is that we not only have the form representations, but also have the labels of the matrix?
I would say yes. You can think of the we can think of the Fourier transform to obtain the blue elements G from the original anions. Also, I want for your question, I want to comment that in non-abelian case, this new Hilbert space is bigger than the original one, because original Hilbert space is not enough to describe all quantum numbers in the condensed phase. Okay. Okay, so let's talk an application of this this formulation. So in this application, we will look at the electromagnetic duality in this Anyon condensation. So the related concept is the Krasmer's-Wannier duality, which is a duality between the ordered and disordered phase in Ising models. It's a duality between the low temperature phase and the high temperature phase. And this Krasmer's Wannier duality is important in the study of phase and phase transitions because it can be used to fix the phase transition point in Ising model, and it can be also used to describe the critical behavior at the phase transition point. And this duality can be also generalized to more models with a billion Ising variables. And also, when Ising model is formulated as a gauge theory, in the gauge theory language, the Krasmer's-Wannier duality can be expressed as the electromagnetic duality. But what we know about the Krasmer's-Wannier duality is about the Ising models or some abelian generalizations of the Ising models. The question is, can we have a more general understanding of the Krasmer's-Wannier duality, at least in our case of the Anyon condensation? So here is the application I want to talk about. So we will study the twisted quantum double phase, which is a finite group gauge theories, a topological gauge field theories with finite groups. And the twisted means we use the three co-cycle in a group cohomology to describe the gauge structure in a twisted quantum double phase. So the issue is, in the twisted quantum double phase, we have anyons as the charge and flux, or charge and flux composites. These are all the anyons in the twisted quantum double phase. And we can we may have many ways to condense the bosons in this phase. For example, we can condense all charge, since all these charge are bosons. But we may also have another ways. We have other ways to condense, like we may have many flux to be bosons, or sometimes the charge flux composites as the bosons. So we have many ways to condense the bosons in twisted quantum double phase. So the question is, if we consider all possible ways to condense the bosons in twisted quantum double phase, and we assume that we only consider the maximally condensed phase, which means after the condensation, there is no topological quantum numbers left. So that means the maximum here. So in this picture, we have many ways, possibly, of the Anyon condensation. Then the question is, between any two of these condensed phase, does there exist an electromagnetic duality? The answer is yes. So in a general twisted quantum double phase, for any boson condensation, we have a global symmetry. We have a global symmetry broken, which is denoted by X here, which may be different from the original gauge symmetry in the twisted quantum double phase. And in a work by Yidong Wang and I, we show that between this G and X, between these two types of gauge theories, that means two different twisted quantum double models, there is an electric magnetic duality, which is formulated as a Fourier transform between these two groups, G and X. And in this way, we show that there exists an electromagnetic duality between any two condensed phase, any two maximally condensed phase in twisted quantum double phase. So this this gives us a kind of a more general picture, not just Ising models, at least in the Anyon condensation case. So
我问一个问题，
yes.
你刚讲的这个 maximally condensed phase 怎么定义？
就是 condense 完之后没有 topological numbers 留下来，就是
没太懂这意思。是指原来的那个群，原来的对称性完全被破缺了吗？
对，
也就是 unbroken 的 symmetry， 实际上就是只有 trivial 的这个 identity。是这意思是吧？
unbroken 的 phase 里面 unconfined 的 states 里面只有 identity， 还要加个 unconfined。
加一个 unconfined， 好，可以了，谢谢。
Okay, so we have talked about the general construction of the coherent state formulation of the Anyon condensation. So let's finish this talk by this summary. Then we also studied the symmetry transform, spontaneous symmetry breaking. So we may ask, as the spontaneous symmetry breaking is related to the Goldstone theorem, then we may ask, can we generalize the Goldstone theorem to the Anyon condensation case? And to what extent we can generalize? So in this slide, we summarize some results about the Goldstone theorem in this Anyon condensation case. So if the condensation data in the topological phase is given by the Frobenius algebra A, and we use the Tanaka duality and reconstruct the hidden symmetry, which is the broken symmetry, the G, then what we have is it's multiple sectors of the condensed phase. So this is the super selection rule, which means in a condensed phase, we can only live in only one sector. And we cannot jump from one sector to another sector. So we only have one physical sectors. And in each sector, we can formulate the condensed states as the coherent states. And as a result, what we obtain is a symmetry protected or symmetry enriched topological phase, since we can explicitly write down the symmetry transformations now. Another feature or another result is when we write down the hidden global symmetry, this symmetry transformation will map from one sector to another. So this is why we call this symmetry a hidden symmetry. And another result of this global symmetry transformation is it makes energy degenerate Anyon species. So this is what we know about the Goldstone theorem in usual quantum field theories. So so in our case, this is like so the energy degenerate anyons means in a condensed phase, we may have different anion species in a condensed phase, which is different from the original anions, and we may have a mixture of these anions. Okay, so that's all I want to talk today. Any question?
我还是想问一下关于那个希尔顿，你那个第一个 label 就那个从那个 ferromagnetics algebra 里来的那个 label， 那个 label 可以是在一起，还要在一起。那个 condensed states， 那个第一个 A 是它是在
第一个 A 是 condensate， 是新的真空态的一个自由度，一个 label。因为你global symmetry breaking 之后，你的新的真空态可能会带你的新的真空态会带一个 global symmetry 的自由度，所以你需要指定新真空的这个自由度。
后面这个那比如说那个最后那个大 N 是，比如说隔点数。
哪个到 N？
就是 V1。
这就是假设你整个系统里面有到 N 个 N 的。
什么要用？是要求新的真空。真空就是
because after the condensation, we may have several sectors of the condensed states, and you can only live in one of the sector, which is called a physical sector. So you have many one states.
就是你们这个，比如能不能用来研究相变的性？就假如有个
希望，
就它这种就是类似于Goldstone theorem这种 additional 的就是这 coherent state 用来 label 不同的 coherent state sector， 实际上是理解像某种 effective theory， 应该是相对点附近的那个 condensate 的那个自由度，就是可以从那个角度出发的。
就希望它这个自由度够了，但是怎么研究相变点的临界现象， 就还没设计。
那有没有算过这个就是星云生态里面那个 effective potential？有没有这个文献考虑过这个 effective
effective potential
对，就是用来研究性能，
只是说
在 symmetry breaking。
零散的可能都会简历 ，minus 自由度，然后再给一个 gradient。
这些模型，我觉得都在0.0 critical point 嘛，这些模型研究的本身是 critical 问题。像不是相变，相变不是这样的。
这是那
这辈子里面
现在没有研究相变点附近的问题，但是这个哈密顿量你可以调到相变点附近，可以就可以去研究。
我其实有点这种，如果你掰这方面，那个 lambda 实际上已经，它是 lambda 是破缺对称性的。
对，
对，所以
lambda
这个相当于不是一个自发破缺。
不，lambda 是保持
的。
那写了，那左边写了。Operators invariant on the global symmetry， 在这里就是 the symmetry means preserve charge number， so W always creates a pair of not just one copy of。
那你记得有地方说那个 Wn 会相当于会多到一个 coherent state， 在那个 coherent state 前面那个
自发破缺是在态上才破缺，但是这个算子本身是保持 Z2 charge 的守恒 ，Z2 charge 是守恒的。
我理解就是你有个 coherent state 那个 wave function， 然后那个 wave function 前面可以有一个有个 coefficient 就比如这个地方到底是 one plus 也还是 one minus 这个是 symmetry
对 ，spontaneous symmetry。
然后那个 W 它有两个 value。
对，
所以我如果指定那个 lambda 的话，那就那很多年人指定一个 lambda， 它这个
就只有一个。
哦，那这个那个 lambda
不是说错了，那是你要选正号还是负号，是要靠一个很小的一个脑洞，或者是加边界条件，这里没有写。就是 W 本身在哈密顿上是保持对称的，保持对称性的。你要选正还是负的那一只，要看边界条件，或者是无穷小的脑洞。
你这些离散对称性有什么Goldstone定理？
所以是看 super selection rule， 从这个意义上讲。
这个可以可能描述这个 defect。
这个群元素小 g 可以去 label， 可以去做 defect。就相当于，比如超导里面有这个 vortex， 和 super3 里面有 vortex， 那就跟这些parameter coherent state parameter 有关。coherent state parameter 是相当于一个是经典量，是可以描述像 super3 的 vortex， 或者是这里的 topological defect。
就最后你这边就是generalize Goldstone， 也就相当于是说你可以通过构造这个convenience function model， 然后它这个 G 它应该百分之是就是构造这个可以就是reconstruct 是整个这个 C 的这个是这个。
不是 C， 比 C 大，是在这个图里面那个一个蓝色的箭头， 从一个 sector 跳到另外一个 sector。
那么这个就是这个 C 是在这个 reconstruct 完以后的，在这个 reconstruct 完以后的这个东西是。
C 是我们理解这个，我们可以把 top 理解成为一个规范场论的话，那么我们Anyon condensation 之前，我们看到所有的 Anyons 这些量子数，那就对应于规范场论里面的那个对称性，规范对称性，我们叫它一个量子群。如果你有 condensation， 那么在 condensed phase 里面，那个 quantum group symmetry 就自发破缺了。自发破缺了的话，那我原来的那些拓扑量子数就不够了。因为那些拓扑量子数其实是这些量子群的表示的类比，而没有它内部表示空间内部自由的能力。这样的话，它就
所以就是我就 reconstruct 这个 cosmology 以后，回到那个更大的，实际上是既包含了它的，
它就相当于 reconstruct 一些内部自由度，那你能够把 transformation 写出来。
那原则上我在 reconstruct 以后，我也知道了 C 的信息，就是
C 是要先给定的。
C 是必须得。
C 是 condense 之前，就我需要知道是。所以最后是相当于之后的那个。
我提一个问题就你最后这页，这个 C 呢是一个 module tensor category，right？
对，
所以这 A 属于 C， 这 A 是要一个就是 observing 的 Frobenius algebra，right？
对，在我们做的工作里面是 observing algebra， 然后我们也只考虑了boson condensation。
对
，A 是
所以
observing
我就说
Frobenius algebra。
你是不是得要求那什么这个A 本身是个 Frobenius algebra？
这个 A 是没写，这 condensation data 就是 A 就是 Frobenius algebra， 并且还是 commutative 的 Frobenius algebra。
OK， 所以你这讲的 hidden symmetry 呢，实际上是这个 A 我叫做condensable algebra 的话，实际上你这有一个 hidden symmetry 这个 G 呢实际上是这个 Frobenius algebra A 的一个 automorphism，right？
A 是可以理解成为 G 的 regular representation。我忘了提一下，就是我觉得最好的理解方式，一个方式就是 A 是 G 的 regular representation。那 reconstruction 定理就是知道了 regular representation， 就重构出群元素、群变化。
OK， 所以这个 G 呢和这个通常就是比方在超导理论里头，或者大家已经熟悉的这个 symmetry breaking 里头，这个理解还是不一样的，我觉得。因为
是超导里面这个 G 就是 U1。
对，但是超导的这个 U1呢，并不是从这个 condensed algebra 本身看出来的，它是原来我先就给了你一个 lower 的 symmetry，OK？
那 Frobenius algebra 可以看成是它的 object 是波色子 bosons，
是 boson，
它就是 trivial 的 Anyon， 所以是波色子。然后 Frobenius 代数的乘法结构相当于这些波色子的相互作用。
OK，
就是波色子的相互作用的方式，对应于弗洛
我
宾的
的
代数的乘法。
我的意思就是，现在从这个 category 思维的角度来看这个 Anyon condensation，我觉得在某些基础的观念上，实际上还和原来的这个比方场论里头讨论这个symmetry breaking 的话，并不完全一样。那是先给定了一个 global symmetry，然后再讨论这个 global symmetry 里头有一个 unbroken 的这个子群 ，OK，然后我选择这个 Higgs 的卫士，使得这个unbroken 的子群实际上是 Higgs potential 的一个那什么，哎，是 Higgs potential 那谷底的一个对称性。所以
这里是第一，我们还没有考虑 Higgs mechanism，只考虑了 Goldstone mode 对应 ，Higgs mechanism 还没有考虑。
还没考虑是吧？所以
然后第二个就是
你这儿的 hidden symmetry 就是完全用这个 A 来定义的。
因为在我们研究的这些问题当中，对 A 和对原来的拓扑态的量子数已经了解的非常好了，它是比较好解的问题，所以我们这方面的知识比较多，所以是从这么来的。
对，所以这个提法我觉得虽然和以前有类比，但是思路实际上还是不一样的。我觉得
对，
这个
但是概念我觉得可以对起来。如果是你从这个 superfluid 的话，那这个 C，你如果是从 Borel transformation 的 formulation 的话，那 C 就理解成为那个波色对义子的代数。
OK，所以在这种体系里啊，你这个强调这个 Tanaka duality，我觉得还是很对的，因为这里头实际上你这红字这一条里头就需要 Tanaka 的 duality，换句话说就是说，我们给一个这个commutative 的 absorbing 的 Frobenius algebra of 一个这个 module tensor category，right？ 然后我就可以提一个问题，就是这样的这个 Frobenius algebra A 是不是一定是某一个 group G 的表示？我觉得这数学上一定是需要一个定理的 ，right？
所以我们是先从能做的去做起，就是 absorbing Frobenius algebra 就一定保证 Tanaka duality 就可以用了，就可以 reconstruct 出来了。
对，所以假如不是 absorbing 的话，这个还不一定对，对吧？
它也对，就是那
假如
就要
我们
更复杂
知道
的情况。
这个 A 本身，问题就是怎么找出来那个时候 A 的这个 automorphism group，right？
对，那是解方程。你就我举一个比较不抽象的例子，就是我们知道所谓的 C 级系数的话，你就可以在电脑上，你就假设任何一个矩阵跟这些 C 级系数是对义的，把这些矩阵全部解出来，就刚好就是群元素的对应的这个变换矩阵。有几个群元素，你就能解出几个这样的跟 C 级系数对义的矩阵。
对，所以就是说，从逻辑上来讲，事先知道这个 A 的话，并不马上就知道这个 G，right？ 还要有一些 technical 的处理。
要
这个 和通常的这个 symmetry breaking 的图像，并不完全一样，因为通常的话是先假设我有一个 global 的 symmetry G，然后我说我要这个把这个 G break down 到这个它的一个 unbroken 的 group，就和这个 category theory 的观点来看 Anyon condensation 思路，我强调就是思路是不一样的。
我觉得在 BCS 超导里面，你也有假设，有假设你做 Boglu-Bol transformation，做完之后你要检验一些自洽条件。就
OK，
Boglu-Bol transformation 能给出正确的 condensed phase 的那些态，你要检查一些自洽条件。那些检查自洽条件跟这里面的这种 reconstruction 就有类似的地方。
所以你这儿讲的自洽条件，就是要形成一个这个产生消灭算符对应关系这些是吗？就是原来伯克利波夫变换这个，你指的是哪些自洽条件？
是理解是，就这个 Boglu-Bol 变换，它确实它产生它导致的那个 condensed phase，就是你想要的 condensed phase，就是那个就你从一个假设从一个 Hilbert space 出发做 Boglu-Bol 变换，但是你最好要检验你这个假设的 Hilbert space 是你想要的。
我没全懂你说的什么叫你想要的。
就是我觉得也是要解一些的，就是我不知道有多大程度上是吻合的，但我觉得也是要解一些这些像 reconstruction 的工作也要解一点，在传统的长段里。
我觉得从前的话，那个波克柳波变换要求，也就是这些新的这个就叫 quasi-particle 的产生消灭算子，就满足这个通常的这个玻色子的这个产生消灭对于关系，就是以前波克柳波变换里头。
是。
所以他就得出那个变换的系数都是一些 sinh 或者 coach。
是。那这个思路呢，就相当于你说先把这个群元素写出来，这群变化写出来。群变化写出来了之后，你再检验这个群作用在 A 上面，是不是 A 表现？是不是就像 regular representation 一样表现
？I see. OK. I got your point. OK. Thank you.
感觉这个产生算符好像就是是说在一个格点上突然冒出一个 E， 然后和那个格点上的 Anyon 进行fuse， 像那有没有对应的页面算符？
因为这是个 Z2 的对称性，所以产生湮灭算子是分开开，你可以当时是一样的。
那如果
你产生湮灭算子是在玻色算子、非米算子下定义的。我这里的话是，我觉得不能完成类比，或者你就把它当成既是产生又是湮灭算子。
如果是 Z2 的例子，就是你再作用一次，就是因为产生算符和产生算符它就是两个产生算符， 所以它是自己。
那这个除非是它什么 recover 到这个就是 C 更大的那个，这个过程是线就是从那个 A 就是 recover 到 C 这个过程，到更大的
到 G
到 G 啊，这个过程现在有就是
数学上很多，
数学上还有就是刚刚那个还是那个产生上的问题，为什么那个前面那个就是那个condensable 的那个指标 A 上面也是错，它是那个在这个位置上产生一个那个 charge 之后，那个 charge 之后会在那个导致结果就是新的那个broken 之后的那个真空上面产生了一个 charge，然后和原来的那个 A 进行去死，就是最开始那个 W 算符合作用。
啊，对，它会作用在 ion 上面，同时也会对真空进行作用。
那个 T 和 D 那个例子，就是那边考虑是那个就是最大的 condensable 的 output，所以它 condense 完那个 phase 是个 SPT，所以就是那边说的那个，上右边是那个 EW 撇D 欧米伽撇，然后是那个是右边那个东西，那边那个 T 和 D 模型相当于是一个 SPT gauging 过程。
是因为你从一个某给定的群 G，一个像 T 和 D，就是相当于一个规范层出发，但是如果你把所有的 G 的 charge 给 condense 掉，那么你最后得到的 symmetry 方这个 broken 的 symmetry 就是 G。
对。
但是如果你 condense 一些 flux 或者是 charge flux components，那你的 broken 的 symmetry 就不是 G， 所以叫 X。G 跟 X 差在这个系统里差一个电子对比。
所以这个电磁对偶就是gauging 过程的话，这个是很浅的 gauging。
gauging 的话就是你把这两 charge 跟 flux 同时考虑，那就是 X 跟 G 的两个不同的群，但是它们的 T 跟 D 引起你的这两个 phase 是等差，它们 species label 不一样，那它们整个 atoms 的集合是等差。
对，就是为什么那个从意思为什么从 SPT 那边重构出来的那个topological order 一定和前面和烟比。
因为前面其实还有，就你的出发点是有这种错，你只能是从同一个 T 和 D 里出发，它两个 massively condensed， 这个要求是比较严。
那问一下，就是因为就是脑的低点，想要研究它的这个 EM-duality， 就是原则上我们应该在这个 reconstruct 出来这个更大的这个，才能完整的
你要看研究什么，
就是 EM-duality。
你可以研究 fixed point， 也可以研究相变点的临界现象。
就是能变得像低点，就是可以直接就是简单的看出它非常完整的EM-duality。就比如那个F3，它有8种类点，我就是看上去好像是没什么对称。就是如果我们想要非常完整的去研究这个，就是去研究这个EM-duality，是不是原则上得看这个是 reconstruct 可能更大的带有这个认为这个对称性。
如果你只是完全看 topological numbers 的话，我觉得
就是还是问你想研究 EM 下面的在哪些系统的什么 face 上面？哦，我有一个很麻烦的问题，这个有 calculus model 吗？这个有 calculus model 吗？这里面是不是这题结束了？
表情更难听，是大概听不懂，不知道你在说啥。
可以说的。
好，
不好意思，
Thank you.